Hello, everybody. Welcome to PhD defense of Evgeny Baraboshkin. The topic of the PhD thesis is automated core description based on computer analysis. Thank you for jury members for participating in the PhD defense. Elena, should I do some introduction about the procedure? Okay, what we will have today, first of all, I will do a short introduction of jury members and the candidate. After that, Evgeny will give a presentation about 40 minutes, followed by question from jury, question from general audience in the room if you will have someone or in a Zoom. After that, we will give a word to supervisor, and we will go to the breakout room to discuss a PhD thesis defense results, and we will announce to the candidate outcomes of PhD defense. Okay, let's start with the introduction of jury. I'm Alexey Cheremisin. I'm a chair of jury today. I'm a professor of Skoltech Center for Petroleum Science and Engineering and also deputy director of the center. I have more than 15, maybe more already, experience in the oil and gas industry, including some service companies, Schlumberger, including academia. My research is focused on chemical, gas, thermal, and hybrid enhanced oil recovery methods, multi-phase flow, porous media, geomechanics, digital rock, and we have a number of different research projects. I have more than 125 publications, and H index is 15. The next jury member is Professor Armstrong. He's a professor in the University of New South Wales in engineering department. He has more than 12 years of experience in oil and gas industry, again both in industry and academia. His research is focused on multidisciplinary research with aspects of applied mathematics, petroleum engineering, computer science, and fundamental physics. Professor Armstrong has more than 180 publications, and H index is 44. The next jury member is Dr. Mohammed Ebadi, who is, by the way, PhD, defended PhD in Skoltech, and he, as I remember, he was a master student in Skoltech as well. Now he's an associate lecturer at the University of New South Wales in engineering department. Dr. Ebadi has more than 10 years experience in oil and gas industry, again, both academia and industry. His research is focused on a pore scale physics, combines various imaging technologies with advanced numerical simulation to investigate and calculate the physical and fluid flow properties of porous media by using data science. Dr. Ebadi has more than 20 publications, and H index is 13. The next jury member is Dr. Harishidiyat. I apologize, I maybe made a mistake in the pronunciation. He's a postdoctoral research fellow in the Geoscience Department, College of Petroleum Engineering and Geoscience, Kinfat University of Petroleum and Minerals. He has more than 9 years industrial working experience as development geologist, geophysicist, exploration geologist, and seismic interpreter. His research and working area includes seismic geomorphology and stratigraphy for petroleum prospectivity and geohazards and other natural resources. He has more than 37 publications, and H index is 8. Next jury member is Sergei Stanchis. He's a senior research scientist at Schmidt Institute of Physics of the Earth of Russian Academy of Science. Professor Stanchis has over 30 years of experience in oil and gas industry, again both industry and academia. He was involved in the development of Schlumberger Center for Geomechanics in the United States. He has some experience in Germany Institute, in Academia Institute. He has a wide area of research interest in rock mechanics and petroleum engineering, including study of fracturing process, dynamic during advanced geomechanical testing, laboratory study of hydraulic fracturing, laboratory verification of model applicable for enhanced oil recovery. He has more than 80 publications, and H index is 29. Okay, let's move to the supervisors. Evgeny's supervisor is Dmitry Karatiev. He's a full professor at Skoltech Center for Petroleum Science and Engineering and founder of and CEO of Digital Petroleum Company. Professor Karatiev has over 20 years of experience in oil and gas industry, and serial entrepreneur, so understand. And his experience focused at 3 domains, including applied artificial intelligence, technology development, and innovation management. He has more than 60 publications, an H index of 18. Co-supervisor of Evgeny is Denis Orlov. He's a senior research scientist at Skoltech Center for Petroleum Science and Engineering and co-founder and BDO at Digital Petroleum Company. Has over 19 years of experience in oil and gas industry, both industry and academia. His scientific interest in Skoltech is related to hydrocarbon recovery and oil and gas field development optimization, including digital rock physics with machine learning and deep learning approaches. He has over 80 publications and H index of 10. And now PhD candidate, Evgeny Baraboshkin is a PhD candidate at Skoltech Center for Petroleum Science and Engineering and Deep Core product owned by a Digital Petroleum Company. Mr. Baraboshkin has over 8 years of experience in oil and gas industry, again, some industrial experience in academia. His scientific interest in Skoltech is related to machine learning and computer vision application in geology. He has over 20 publications and H index of 5. Thank you. If we don't have questions about jury members and we have a quorum, as I understand, let's move to the candidates presentation. Evgeny, floor is yours. You have 40 plus minus minutes.
Thank you for the introduction. Today I will tell you about my research results on automated core description with computer, based on computer analysis. And we'll talk first about the research which we can find in the field. Then we will switch to the methods which could be applied for geology description from the computer vision, then how the data could be collected, and about the algorithms, classification and segmentation algorithms, which were applied during the research, and about the system construction, which includes both algorithm for segmentation and classification. In the end, we will go through conclusions and switch to discussion and recommendation for future research. So to start with the problem statement, the main problem for now is that most geologists use laptops or some special tablets for which they fill during the research. And it takes quite a lot of time to describe the core precisely. That's why sometimes the core reinterpreted by several experts several times, and it takes even more time to process the core. And the thing is that the core is the initial information, has initial information about the deposits studied. And if you lose some information from it, then it may influence on the further development of the deposits. So what we want to do is create an algorithm which will describe the core quite fast and reveal the information about the core much more easier for the expert and give him much more time to think more than to do the description. So there are quite a lot of researches about the core description by different computer vision approaches. They could be classified to 3 big groups. First is machine learning and computer vision application, which is based on the application of different algorithms which could classify the images in different ways. The other group is computer vision methods, which are based on color distribution analysis, and the expert could set the various characteristics about the colors which are segmented on the image. And the last group is deploying and computer vision methods, which are applying already more advanced techniques of machine learning. So all of these studies are aimed to increase the speed and precision of the finite geological model and decrease the time to develop the deposits. There are several questions which could be raised while you describing and analyzing the literature. First, is it possible to describe the core automatically with sufficient speed and precision? For some reason, not all of these methods described before were applied as some kind of software. Also, another question, which characteristics could be described? And this is a really interesting question because you can describe quite various types of and extract various type of information from the image. Also, what is the best algorithm and approach we can use to tune it to the data we have, and can the algorithm could be implemented into some kind of a system which could be used by the expert. Also, it is a big question which way of implementation is the best. That's why various architectures and various implementation ways could be done during the research. So the main aim is to make a tool which will describe rock lithotypes automatically, which will increase the precision of geological study, the value of information and finite geological model quality, and decrease the uncertainties about the reservoir, cost for reservoir development, and time to get the geological model. The first problem for the researcher, which he can bump into, is the terminology, because almost each geologist and computer vision computer scientist expert has its own opinion on the terminology. That's why we will use several main terms during this research. The first one is lithotype, which is a type of rock which can be identified by a number of lithological features. Computer vision, which is a transformation of data from a still or video camera into some kind of decision or a new representation to achieve some particular goal, and machine learning, which is about extracting knowledge from the data. So various methods were tried during this research. Both supervised and unsupervised approaches were implemented with use of various well-known libraries, various feature extraction methods which help to extract the information from the image, and also some methods for segmentation of the image to extract the information from the image and classify it somehow. Also, deep learning algorithms were used for most of these tasks as additional help to the algorithms. To analyze and correctly describe the dataset and the results of the experiments, several methods were used. It's accuracy, precision, recall, and confusion matrix for classification, and mean intersection over union for segmentation. And I'll stop a bit on this confusion matrix because it's really important to analyze these data. For example, we have some kind of expert-defined labels, which we introduce to the algorithms, and the algorithms can predict some kind of classes during the inference stage and during the training stage. Basically, we have some false positive and false negative results. And during the analysis of such table, we can both control the expert which defined the classes here, because some of them could be for some reason placed in the wrong labels, and control the algorithms which also can do a lot of mistakes during the development of the algorithm. So first thing, as I said, is to prepare the data, and it's quite big thing to do because in geology there are, as I said, different experts can produce various results and various descriptions. That's why several tools for data checkup were developed. First is to correctly reference the depth for the core boxes. This one is used by the expert, which fix the depths during the analysis of each image to better classify the image which is on his screen. The other tool is for data checkup. In the left side we have initial data, and to the right side we have data which was classified by the expert. So during the data checkup, expert goes through all the data set and checks the labels for each image. And after such data cleanup, quite a lot of data may be reinterpreted. Here are the results of such action. And we have some unlabeled data which was transformed to some labeled data by the expert. And 4 datasets were prepared by such methods for rock typing, for sedimentological description, and 2 datasets for geotechnological description. So 2,860 meters were analyzed in such way to prepare the datasets. And as it can be seen, the data distribution is quite uneven, which could influence on the step of algorithms training. But applying special methodology, we can fight this issue. Another dataset preparation was the segmentation step for segmentation algorithms, and it is a manual labeling based on a special tool, which is apply watershed during the segmentation by an expert, and 250 images were manually labeled with such methodology. And another approach to data labeling is manual data labeling in various GUI applications like GIMP. And here expert manually labeled several labels like core, like scale here, and so on. And 1,000 images were initially labeled in such way. So going to classification application, several methods, as discussed, were applied to test various approaches. First is PCA, then principal component analysis. HOC is histogram of oriented gradients, and pre-trained neural networks were used to extract the features from the images. Also, convolutional neural network was trained to compare these various approaches, and the features were classified by SVM and random forest, and these results were compared. As could be seen, which is quite interesting, that support working machine classified the features extracted by this one, a convolutional neural network, much better than a convolutional neural network itself, which could be used for the future algorithm development when the data amount is quite small. Convolutional neural network could be used for future extraction for SVM algorithm. Also, unsupervised methods were applied, and as it can be seen, they worked on this dataset quite poorly, but this could be because of various reasons like cold distribution changes in various parts of this dataset and many other things. The convolutional neural network was also kind of unboxed, as most of machine learning algorithms are thinking to be black box. We analyzed the features from the network, which it is analyzes during the classification stage, and as it can be seen, various algorithms, various architectures extract various characteristics from the images. So it could be structure, it could be texture, and so on. And it's very important to understand what is important for the algorithm during the classification stage, because while training the algorithm, you can especially augment the images, change them in different ways to better generalize the algorithms during the training stage. Several classification algorithms were trained, as for example here is sedimentological algorithm, which describes rock type and structure simultaneously. And as it can be seen here, it's not always easy for the algorithm to defer various structures or textures, but it's much easier to defer various rock types. So most of mistakes here are made inside the same rock type, so all rock types were defined correctly, but some of them, the structures of this rock type were misinterpreted by the algorithm. This is caused due to multi-label use of these classes. Each image contains several labels, like lithology, rock type, and structure simultaneously, and this information also could be used for better algorithms training. The next step is segmentation, and these algorithms were developed actually a little bit earlier, because most of data which was collected is stored in core boxes, and as can be seen, because we have quite various core boxes stored in each core facility, and we have different standards for storage and imaging of these cores. It is really hard to train a good algorithm which will segment correctly some new unusual data which wasn't used during the training stage. This could be caused by color change, lighting conditions, separate various core columns, color, and some other issues. To fight this issue, a special augmentation algorithm was developed, which changes some parts of the image based on the initial mask. And as you can see here, the core column could be changed, the background of the cores could be changed, and the foreground also could be changed. For example, here this head was placed on the image. We also made some questionnaire in social networks and showed several types of augmented images together with the real one, and asked people to detect which one of these is the real one. And as could be seen, not all of them answered correctly. So even human may mix the images, and the right answer here is the number 4. And such an approach, as can be seen here, allowed us to increase the mean intersection or union from 0.66 to 0.93. It's on these matrices are gained on the new data, which wasn't showed to the algorithm before. And another thing which were researched during this work is the segmentation of rock types. As I said before, that's not quite a lot of images for training were used, only 200. But even with such small data set, it was possible to get quite high for such small data set matrices of 0.52. Also, various unsupervised methods were applied to compare the results, but as for each image and for each dataset, we should tune the algorithms. It's much better to apply the convolutional neural network, even it's harder to develop the algorithm for classification. Then all the algorithms were united in a system. So the main idea here is to first use the segmentation algorithms to extract the core columns and reference the depths, and then do the data labeling with classification algorithms. Well, the idea is simple, but the methods how it could be implemented could differ. So several software architectures were tested. First is local, and their other is web application. There are some pros and cons. For the local version, it doesn't need any additional infrastructure to support it, but it's hard to maintain it, it's hard to update it, and there are several licensing issues which are important which for the company if it starts to use it. And the web version, it has some pros as easy maintenance, easy to update, and there is no licensing issues. But there is always need some kind of a server which should be maintained by IT team. So the final product was developed together with Digital Petroleum team, and as it can be seen here, the system available online for test for everyone, and there is no need in installation, and it is easy to update. And also, if amount of users will grow, it's quite easy to scale the amount of algorithms which are applied during the work of the system. But of course, it's some kind of infrastructure should be maintained, and the IT team should support everything almost continuously. So based on this product, several tests were run with various companies from both oil and mining industries. And here are some results. So as can be seen here, the matrices are quite similar to tests results. And the overall net to gross calculation are quite also similar because of this effect which I mentioned before, that most of errors are only between structures but not the rock type. So basically, these algorithms could be applied for very fast core analysis, even without expert much involvement. And then the expert could further check the results and add some labels which are not in the model. And then the algorithm could be additionally trained on the data which expert give to the system. So in overall, this system application speed up the core description in 7 times. When expert describes the core in usual way, he spends around 5 hours in total, and when he uses the system for description, he spends only 40 minutes, both for data checkup and depth referencing. The other application which was tested is from mining industry, and it is for waning detection on the image. The same way as in previous results, the expert checked the results of an algorithm, and the precision is also quite high for the dataset comparing between 2 experts. Again, this algorithm could be applied for quite fast and easy data analysis. So what are the constraints of this system? First, as I described, the core should be quite well prepared to create the model. The description should be checked, which could be difficult for some experts. And not less than 100 dpi resolution should be on the images, which is about 400 pixels of column width for 10 centimeters core, and for 250 pixels for 6 centimeters of core. Basically, this restriction is not a problem because most of data, even archive data, has much better resolution. So to build a classification model, at least 10 meters of core for each class is needed, because if we will have less amount of data, then the algorithm will receive much less confidence in its predictions, and it is possible to build a model which will classify images with different lighting conditions, but the dataset should be much larger, not 10 meters, but hundreds of meters for each class. So which are the conclusions of this work? Well, first, the work is the pioneering use of convolutional neural networks for lithology classification and core image extraction, especially for the last one. Also, various experiments were conducted during the research, and compared all these algorithms were tested on some new data. So the results are tested widely, and new methods were developed for data augmentation. Also, full image analysis performed from the full Bohr core extraction to data classification. Possible ways to estimate various characteristics like net pay ratio and RQD and so on were tested and presented. And various application tested also, both in mining and oil industries. And of course, the software product was released and successfully tested, which is quite good for the research. What are the recommendations for future research? When the data will be enough, it could be tested various approaches for algorithm training, like multi-label class, application of different algorithms. Also, semi and unsupervised learning could be applied when the data set will be enough. Maybe this will change the results which were gained during this research. Some additional data may be added to the data set, like well logs, to increase the the description accuracy. And also various lighting condition could be added, like UV images and so on. And the developed core box segmentation algorithm also could be improved with adding various labels, like number and depth labels and scales, which also could improve the overall experience of the user when he uses the system. Various publications were published. Some of them even received quite a high citation rate. Also, the results were presented on various conferences. So quite a lot of outcomes were presented before, and they received quite good reviews. And a lot of people contributed in this research by their comments, their knowledge, and their interesting insights from the industry. So the research has quite a big impact on the industry because the product helped to increase the geologist's productivity. It increases the quality and decreases overall time spent for core description, and helps geology to think more about the data results than about the data collection. This increases precision of geological study, the value of information, and finite geological model quality, and decreases the uncertainties, the cost for reservoir development, and time for getting a precise geological model. That's all what I wanted to tell you about. Thank you for your attention, and I'm ready for questions.
Okay, Evgeny, thank you. Very interesting work. I would like to highlight that it's very important that it's both academic research and industrial applications. Congratulations with this. Okay, let's move to the question from jury. I'm as a jury chair, will ask you a question first. First of all, again, thank you very much. It's very high level work. Right now, a lot of, especially in oil and gas industry, I'm not sure about mining industry, but a number of additional advanced tools are available, like multi like 360-degree scanners, or some ultraviolet scanners, or even in most companies, what they're doing, they combine both photo fixation and X-ray CT scans. How you can use this data to better classify, or maybe to distinguish some additional features of pore space?
Mm-hmm. Yeah, well, this kind of data could be used, but as most of companies store it inside of them, it's hard to get such data. And the other problem is to reference this data together, because sometimes they are imaged in different conditions.
Okay, thank you. But my recommendation would be to try to combine both of them.
Surely it will improve the results. Thank you.
And also, one of the question about when you compare your results from which was predicted by your algorithm with the expert data, you choose to compare NTG, but it's only one parameter. Why you didn't compare, I don't know, the amount of lithotypes or some kind of advanced statistical data?
Well, the advanced statistical data was also used during the research, but the NTG as some kind of general characteristic could be applied directly in the geology model. So we, of course, compared both the precise of description by the lithotypes and NTG to make some kind of a showcase for everyone.
Okay, thank you. And my last question will be, you show us the difference between algorithm and expert. Did you try to measure the distribution between experts' opinions?
Yeah, we did. Actually, these are quite recent results, and they could be, well, the precision between two different experts could be from 50 to 70 percent of accuracy.
And between three experts, like
Yeah,
thousand?
that's an interesting thing to compare. Yeah.
Okay, thank you very much, Evgeny. And I am fully satisfied with the changes were introduced after my review. Thank you. Let's move to the next jury member, Professor Armstrong. Please, questions. Can you hear?
Hello, I'm here. Yeah, some reason, there we go. My camera, I had to select something else for it to get started. Okay, I think you should be able to see me now and hear me. Yeah, so thank you very much for your presentation. One thing I really like is that you've tested so many different methods and really evaluated these methods over a lot of interesting data. So it's a really nice collection of the capabilities that not just machine learning, but deep learning and so forth can do for core analysis. I do have a number of sort of specific questions and maybe some more general questions. Maybe you start with the net to gross calculations. I understand that you reported the percentage for the net to gross, but I'm wondering, this is an average value. So I'm wondering, is there some sort of like intersection over union sort of measurement you could do to compare the two to see if they're actually identifying the same regions where the net is, or because I'm wondering if net to gross, all the errors could average out and it could come out to give a similar result, even if the region characterizations are quite off.
So,
Could you comment on this?
So the question is, did we can the NTG be calculated in some certain regions, right? Or
yeah, so NTG, my understanding, this is average value from the log analysis, but it's based on the local measurements of what the rock type is in this region. So do you have some more local sort of measurements to show that the measurements are correct locally?
measurements of cracks, right? Or
yeah.
Yeah, we do have such measurements. They are not presented in the research. We calculated RQD. It's widely applied in the mining industry. And the rock quality designation is also could be calculated based on the other algorithms implementation for core condition description, for example. So yeah, it's a geotechnical model which could be also applied, and then the same way as NTG could be calculated in various scales along the whole core.
Okay. When working with the unsupervised networks, the clusters that they generate, do those clusters end up having much geological meaning? Or can you comment on that a bit further?
Well, no, they didn't. They more classified probably various structures, various lighting conditions, but not. There is no information for a geologist to which could be feasible for him. Unfortunately, yeah.
When I was looking at your thesis, it seemed like some of the training data was pretty imbalanced. So I'm wondering, you didn't really mention it here, I think in the presentation, but I'm wondering what strategies did you use to compensate these imbalances and what influence this might have on your results?
Well, there was several strategies. First is applying of augmentation for those classes which are underrepresented in the initial dataset. Also, there is several methods based on additional picking of the same images, or we could also not use the images which are which has a lot of data in the a lot of quantity in the data. So just balancing the data quantity and do some augmentation.
Mm-hmm. Did you try any methods using weighted cost functions or anything like this?
Sure, yeah,
Or
we did it, and it's well produced. Also good
did it
results.
help? Or I'm just wondering, I know from our side we see mixed results sometimes with using it. So I was wondering from your experience what you found.
Well, the weighting could influence on the testing set results quite nicely, but sometimes if you weight the class which has quite small distribution, it could cause bad results for the new data. So the distribution is not enough for generalization of the algorithm.
Okay. How you explain the sort of deployed software? It seemed like the applications were very local to certain, like to a certain client. Someone may come in and have a project where you do machine learning and you do the analysis and then that's done. But I'm wondering, did you think about strategies on how the information from previous clients could be used and how trained models can be, updated and transferred to future clients' projects? So, information and the projects that you've had in the past are helping you inform future work.
Yeah, well, thank you for the question. It's interesting thing. Well, first we can use the open datasets to collect some information, some additional classes which we could introduce to the clients. And in most cases, clients has some databases which they previously prepared, but it's always a need to reinterpret these datasets because they could be collected in various times by various peoples. That's why the classification could differ between the databases. And during the application of the system, the expert changes the results inside the system, and we can use these changes to better train the algorithm in the future.
Okay, yeah. So it comes down to, I mean, what the extrapolative power is of these methods as well, I guess. So I was wondering, based on your experience, what's the future limit for the accuracy and precision of these deep learning models? Do you think they've plateaued in the accuracy for image classification? Or do you think it's still a lot of potential there?
Well,
in the development of, say, new architectures or cost functions, loss functions, and so forth?
Yeah, well, it's interesting questions. Of course, we can experiment further with various architectures, with various matrices, and in terms of the Plato, maybe sometime we will have some kind of Plato which could be similar to two different experts' accuracy. But of course, we need much more data, much more experiments, and this is subject to research.
Let's see. I think I've asked most of my questions I had. Yeah, maybe one last question. Let's say, after you're done here with your PhD and you're maybe on some advisory committee for a data analytics project, under what circumstances would you advise to use, traditional statistical models versus machine learning versus deep learning?
Well, I would say that the traditional statistics may be only applied if an expert knows what he do. Yeah, because as was shown, there are some computer vision methods which are applied for core description, which are based on cold distribution analysis, and they're working well, but they are taking much more time to apply for an expert than the deep learning and machine learning algorithms.
So when should I mean, under what circumstances should I actually employ plan to use deep learning? So, I mean, what would be the requirements?
Well, the main requirements is decent amount of data, like at least hundreds of meters of core, and certain amount of time to train an algorithm. But after the training, you can apply it almost on any kind of data if you do it in the correct way. That's the main preference of such algorithms.
Okay. Maybe just one last question. So I know at the end you mentioned the using sort of multimodal data and so forth. Would you envision that as, having independent networks doing predictions and trying to put those together? Or would you envision that as having a single architecture that all the information is coming in to the input nodes and coming out with the prediction? What sort of structure are you thinking about multimodal data? Would be interesting point of discussion, I think.
Yeah, well, if we have enough data which will describe all this amount of rock types and all this amount of lighting conditions which we can have in the dataset, maybe sometime we can produce some kind of general artificial intelligence which will do all the work for us. This will be nice. But well, currently for that amount of data which we can get usually from various data sources, it's better to train some kind of algorithm for each type of characteristics, and then maybe analyze those characteristics produced by the algorithms and somehow combine them in kind of a smart way. For example, like we have some rock with maybe some wane, and we have if the others algorithms tell us that there is no wanes in this image, then probably the decision made by two other algorithms could be wrong.
Yeah. I'm wondering if there's also potential within the real language models. This is a pretty hot topic the last couple of weeks as well, of taking like geological reports and sort of incorporating that information into further prediction. something
Yeah, well,
might be interesting.
it is possible, but there are some applications which were developed previously, which just can take different characteristics and make the same report as geologist will do.
Yeah.
Yeah, you can use the classes produced by the network to create such report.
Yeah, that would be quite interesting, I think. Okay, great. Thank you for that. I think I'm all done.
Okay, Professor Armstrong, thank you for the discussion. I have a question for you. Are you satisfied with the changes introduced by the candidate after the review?
Oh, yeah, I forgot to mention that. Yeah, I'm satisfied.
Okay, thank you. Let's move to the next jury member, Dr. Ebadi. Please, your questions.
Yes, can you hear me?
Hello.
Okay. So thanks for the presentation. Clearly, a lot of effort has been put into the research. So I have two questions regarding pre-processing and also one of your papers. For the first part, for pre-processing, I had already mentioned in my report that you have used PCA for transformation. And so PCA, at least up to what I know, you are going to choose the number of parameters or number of classes that you want to have as the output from the PCA. And so it's not that much selective for you. But my question was that if you are going to use Fourier transforms, so you have this chance to select which frequency you want to have. So have you tried that one or any other transformers?
Well, yeah, various transformers were tested during this work, but they produced quite similar results as the distributions of the images in the data set is has quite different and quite various frequencies in each image. That's why it's quite hard to describe it in terms of frequencies, and most of the feature extractors produced quite similar results.
Mm-hmm. Okay, so actually, figure one of your thesis, which you have the original image and then the result of applying PCA, it shows that PCA is gonna make kind of pre-segmentation style to your figure. So the question, which is going to be the next one here, is that if we are going to have PCA and if the result is that much nice, so why not applying like kind of simpler classifier like KNN or K-means?
Well, and that's for the segmentation, right?
Yep.
Well, yeah, the thing here is that the color distribution in the dataset is also changed from time to time, because the rocks could be of different colors with different saturations. That's why not always simpler classifiers could get the distributions and to classify the segments correctly.
I see. Actually, this is also the reason that why we cannot apply Fourier transform here, because then we need to select the frequency, and then case to case is going to be different. And about the paper from your thesis, which has, I think, I don't know, good number of citations right now. So you have used CNN for labeling there. So I wonder why you have not applied image-to-image translation like SegNet, like similar stuff to SegNet, ResNet, or UNet, So the question here is that if we are going to have like those image-to-image translators, do we still need to process the data, the images, with all those filters, or no? You tried those image-to-image translators and it still not worked.
Well, yeah, I did apply it various image-to-image translations, and there is also an example of it in the segmentation. But it's quite hard to prepare the dataset because it requires quite a lot of time to segment and to segment all these features on the image by the expert. That's why it's easier to classify just classes, not the each pixel of the image like that. Yeah. But of course, if enough data we will have enough data for that, it will help to better to create better data set for geological model.
Okay, I see. Okay, thanks. I'm done. And thank you for correcting all those comments in your thesis. Nice.
Thank you.
Thank you, Mohammed. Okay, let's move to the next jury member, Dr. Harish Dayat. Can you hear us?
Yep.
Please, your questions.
Just a moment. Can you hear me?
Yeah. Hello.
Yes, very good. Thanks. Thank you, Evgeny, for interesting presentation. Very good thesis. I have some couple of questions regarding your thesis here. Maybe we can start for the first one. So in the chapter 4 of your final thesis, you mentioned that this technical core condition description was developed to build a reliable model for the fracturing detection. Yes, how reliable is the algorithm that you built or the model that you built for the fracturing detection? And also, we know that geologists made a label for this fracture, and we know that some basin has local tectonic process as well. How reliable is it?
Well, the average precision, as far as I remember, is around 70%. So it's quite reliable. And interesting thing here is that the algorithm was initially trained on 6 centimeters core diameter images, and it could be applied on any types of core data, because the features which are analyzed during the image analysis by the algorithm are quite common for any type of datasets.
Okay. Okay. Then related to that, on the general discussion and conclusion, you mentioned that the accuracy of such a method is up to 95% and may depends on the geologist's opinion. What kind of geologists here that you mentioned?
What kind of, sorry?
I mean, like knowledge, like a level of knowledge.
What kind of knowledge?
Yeah.
Well, geologists had some background in, for each algorithm we took various geologists, which are better suitable for the dataset classification. So the background of the geologists were different. And for example, for sedimentological datasets, colleagues from MIMGOR analyzed the results, and the background is sedimentology mostly for the data set.
Yeah. So it means that it's come to the like sedimentology, lithological classification. We need kind of sedimentologists, and and for the fracture detection, it means that the geologists need certain level of the geological knowledge. That's
Yeah. So for cracks detection, it's usually needed only some geotechnological type of knowledge. So usually geologists should know which types of cracks exist. Is it a mechanical crack, or is it a natural crack, and so on. And for sedimentology, the expert should know what kind of structures and textures exists, and how do they how they could be changed because of some environmental conditions.
Yeah, because I'm interested with your software that release, and just imagine if someone to use that software, and then what kind of calibration that we need if we want to use your software, and we try to use the core from different basin than yours.
Well, it depends on the data, because, for example, the Trigenius core are quite similar from different deposits, because they have sandstones, argillaceous rock types, and they have the same size of particles between various deposits. So mostly you should only have small amount of data to tune the algorithm, and if the data is quite new for the algorithm, then it's better to train another algorithm, and then after its application on certain amount of new data, we can use this new data to further retrain the algorithm and get better results.
Okay, good. Another question is in terms of the conclusion. You mentioned that essential characteristic for further geological modeling. It's mentioned also in the chapter 4 of your thesis. Can you elaborate more on this? What do you mean by this essential characteristic for further geological model? I mean, we as a geologist usually need to build like a properties model, porosity, permeability, saturation, water, and then what kind of what's it called? What kind of essential characteristic you mentioned here?
Well, it could be different. For example, most of rock types has some certain properties in terms of porosity and permeability. So by applying such algorithm, we can detect these rock types, and then with our knowledge of permeability and porosity, correlate it to the rock types.
Okay.
Mhm.
That's all from me.
Thank
Thank
you.
you.
Thank you, Dr. Rishidet. I have a question for you. Are you satisfied with the changes introduced by the candidate to the thesis after your review?
Yeah,
Thank you.
Thank you.
satisfied.
Thank you very much for discussion. Let's move to the next jury member. Sergey Stanchik, please, your questions.
Yeah, thank you, Evgeny, for your very interesting presentation. I have a question regarding your comparison with the expert results of analysis. You presented the comparison demonstrating that machine learning can operate much faster a few times. It's clear, no questions. And you also mentioned that in some cases, your algorithm can show results better than expert. But I remember that when I watched the operation of experts in the core viewing rooms, they used a lot of additional data. They used the X-ray images, they used the photos not only in the visual light but also in UV light, and they use the well logging data, and they just compared all this data. You mentioned to the question of the chairman that you can combine with this additional data, but I remember also very well that in some special cases they even used the magnification glasses to look more careful on the samples themselves, and they also use the even acid in order to put a drop of acid and to see what is the reaction of acid with the chemicals, especially to detect calcite, for example, the presence of calcite. And they also, some experts used even the smell of the rock to identify these production intervals. And therefore, in some cases, expert can include all this additional information in their expert decision based on their many years experience. How your algorithm can integrate all this combination of different data, and how you can propose algorithm which could be even better than expert knowledge?
Well, thank you for the question. So how can we do this? It's of course by combining the various data sources, but in terms of these algorithms which were developed, they are oriented only on visual recognition of images. So here we are mostly talking about those characteristics which expert could detect by his own eyes. Yeah, and that's why the further application of the algorithm in the system implies the changes which expert can do in the results of the algorithm, because not always it is possible to detect some features from the image.
Okay, but what do you think? Maybe you can make a combined, you can propose some kind of combined algorithm that your machine learning can do mass analysis, for example, hundreds of meters really very fast, and then detect some intervals. And then experts with the knowledge can focus only on some particular samples, and then to analyze in more details. And actually, my second question is also about resolution. You mentioned that 100 dot per inch is the minimal resolution, it's clear, but maybe your algorithm can also detect some intervals where you need higher resolution, even to look in more details, and then you can have a loop of feedback. And what do you think? Is it possible to make this combined?
Yeah, that's a good idea. It is possible to do such thing, but it's also will require some additional works to be implemented in the system. So yeah, I think it is possible, but we need some time to do this research. Thank you.
Okay, yeah, thank you. Thank you, Evgeny. I'm satisfied, and actually I can tell you that I fully satisfied with all corrections you introduced to your text of your PhD thesis. Thank you.
Very much.
Thank you, Professor Stančić. Do we have any more questions from jury members? If there is no more questions, we are open for questions from online auditory. Do we have any questions?
No, not at the moment. Even though we have some audience, so maybe if we shall offer to those audience members who have any questions to Evgeny. So please feel free to unmute and ask your questions.
Okay. If we don't have any questions from audience, I will give a word to the supervisor and co-supervisor of PhD candidate. Please, Professor Karateev.
Yeah, thank you very much, Mr. Chairman. So to keep it simple, I'm actually very proud to be part of the research and engineering work which Evgeny has done over the last 5 years, actually working with me and with all of us in Digital Petroleum Research Lab and in Digital Petroleum Company. So Evgeny has demonstrated that he is able to cover all the areas of a professional R&D person. So he did the semi-fundamental research pretty much himself. And this was the really pioneering research in the area of application of deep neural networks to the description of core samples being put to the images by some photography. Evgeny has done a lot of effort into putting his research outcomes into the algorithms which could actually be implemented into the fully functional software. Evgeny had done a lot of research in making the software actually working in the user-friendly way, making it very fancy architecture so that everybody can access the software from all over the world through this cloud application. And also Evgeny has made a very good effort on commercialization of this software. He's a little bit shy, but right now the software is actually used in the second biggest mining company, a gold mining company in Russia, and being tested in 3 more oil and gas and mining companies at the moment. So this is a really unique combination. So research is here, and this is a high quality research. The engineering is here, and that's high quality engineering, and the innovation, including commercialization, is here. So I think the PhD work itself is very solid. It has all the components, especially what is rather unique, the pure innovation component, which is not always in PhD works. So myself, I fully support this work as the one applicable for Skoltech's PhD. And I want to thank all the jury members for being able to either come or connect here. That's a big honor for us to have you all guys here. Thank you very much. That's it from my side.
Thank you. Denise, please, your comments.
Thank you. I just want to support Professor Karateev and state or claim that Evgeny made a really very good job. He prepared not only a completed research, but he also created an industrial tool, a software, a production level software, which is tested and approved in at least 2 industries, in oil and gas and in mining. And another very important point that Evgeny now has more than one profession. He came to us as a master level geologist, petroleum geologist, but now we can see that it is a very qualified geologist, not only in petroleum, but also in mining and even in other areas of geology. He also demonstrated very strong skills and knowledge in everything what we know about AI technologies. He's a very good engineer, a data scientist, very good expert in machine learning, deep learning, machine vision, whatever. And the third component of his professional background for now, it is He's really at least middle-level IT specialist who know everything about front-end and back-end development, DevOps, and all other components of IT industry. From my point of view, the PhD education as it is more about to prepare the independent professional, independent scientist. The institute, the Skoltech, the advisors, they should teach the researcher how to state the problem and how to solve the problem, accumulating all available information and expertise from different knowledge domain. Actually, Evgeny demonstrated that he has very good progress in this area. And finally, I 100% sure that he deserves the PhD degree for sure. Thank you.
Thank you, Denis. Now we are done with all questions, unless we have some questions from jury. If no, thank you, supervisors, thank you, co-supervisor, for your comments. Now we are going to go to closed discussion. As I understand, the PhD candidate, supervisor, and co-supervisor should exit the room, and we will go to closed room in an online session as well. For the general audience, we will go to the special breakout room, but we will come back on the same conference to announce the outcome of the discussion. Thank you. Dear Evgeny, dear supervisors, the jury members vote for to accept your thesis as is, and basically PhD is awarded to you. Again, I would like to thank you for the excellent research, and it's very important part that you apply your research to the real products, and you use. It's already used by a number of companies, as I know, and I hope that you will continue to develop the product. I would like to say thank you to the supervisors. You did a great job. You have a new PhD just awarded, and I would like to say thank you to our jury members. Thank you for your time. Thank you for your comments. On the final protocol, Evgeny, you will have a few comments from jury members just for you to take it into account. If jury members would like to say something to candidate, you're welcome. Lena, should we go with the final words from candidate, from a PhD?
Yes.
Evgeny, or from a
I
jury?
think we had a couple of words from our jury members as well, so maybe we shall give the word.
Dear jury members, please share your comments.
Oh, okay. Yeah, so Evgeny, well done. Congratulations from my side, and also congratulations to the supervision team as well. I know it's a journey together to this process, so congratulations to everyone, and very well done. So what, maybe when you talk later, I was just going to ask, what are your plans for the rest of the day? How do you celebrate?
Oh.
Thank you very much, Ryan.
Thank you.
Yeah, really, really good to see you again. Thanks for joining.
Thank you, Professor Armstrong. Any more comments from jury members? Okay. Evgeny?
Yeah, I can
okay.
say something.
Yeah, we can hear you.
Hello, can you hear me?
Yes.
Okay, good. Congratulations, Evgeny, for very good work, very solid PhD thesis, and congratulations to Supervisor Committee, Professor Korotev, Dr. Orlov, and Skoltex. Very well done. Congrats.
Thank you very much. Thank you for connecting. Thank you for connecting in your vacation day. Yeah.
Thank you.
No problem. No problem. Greeting from Saudi Arabia.
Dr. Ebadi, would you like to give a few comments?
I wanted to give a sentence in Russian, but I have nearly forgotten everything. Just Udachi in the future, first of all. and hopefully you're going to keep working. I know very well how you went through all this stuff, and hopefully see you soon in top levels. You deserve it. Thanks.
Okay, thank you, Marhan.
Thanks, man. Good to see you here.
Okay, thank you. It's we have a comment from jury member Evgeny. Please, if you'd like to make a few comments, you're welcome.
Yeah, sure. First, I would like to thank everyone in the jury for their reviews and for their valuable comments, because it is really nice to talk about the research you do and receive some positive feedback. Also, I would like to thank everyone who contributed to this work, and of course to the product, the final product, where all the algorithms were implemented, and all those people who proposed various ideas during the development and during the experiments we run with these algorithms. It's really a big amount of work from each of you, and thank you very much.
Okay, thank you very much. One more time, congratulations. Now you're Dr. Baraboshkin, and we are looking forward to work with you, and good luck with your future plans.